In this video, we'll talk about the limit laws and other theorems for sequences that pretty much come from the ones we had before for functions. So the fact that the limit of a sequence is generally evaluated by the limit of a function means all the theorems we had before for limits of functions work here for sequences as well. So that gives us things like the following. So if we assume that we have two sequences, an and bn, that are both convergent, with, say, an converging to L and bn converging to M, then we're allowed to combine these sequences in nice ways that give us the way to evaluate more complicated sequences. So then we know things like the limit as n goes to infinity of an plus bn, so I can combine them by adding them, and I get the sum of the limits. I can combine them by multiplying them, an times bn, and that gives me the product of the limits. I can divide them, and that gives me L over M, provided M is not 0, i.e. I don't have a problem by dividing by 0 here in the last step, and I can multiply them by constants. And all of these basically work the exact same way as the ones we had for functions before, right? If a limit existed, then I can do these things, right? If I had two functions f and g and their limits existed as you approach some value c, then I could add them. I could multiply, I could divide, I could multiply by constants. All of that worked for functions. It all works here for sequences as well. The important thing to realize is this assumption. All of this works if I assume at the outset these are convergent sequences. If I don't know that an or bn converge, I can't use any of these properties. This is the same thing we saw before for limits of functions. If I didn't know the limit existed, I couldn't multiply, add, divide, do anything beyond that point. So if I have these limits exist and I know what they are, then I can combine them in nice ways to work out things like this. We also have a version of the Squeeze theorem that applies for sequences as well. What was the idea for functions? Well, the idea for functions was if I had some function f that I didn't know anything about, but I knew that I had a function u of x that sat above it, and a function L of x that sat below it, and they all pinched off at the same point here in the middle, then I knew f had to be there as well. That was the idea of this squeeze theorem for functions, was if I had an upper function above it, a lower function below it, and they had limits at the same point, then I knew f had to do the same thing. The idea is the same here for sequences. So if I have three sequences, we'll call them ln, an an, which is one I don't know anything about, and a un, so that my ln is always smaller than an is smaller than un, and L and U have the same limit, then A must also have the same limit. And this is the exact same as one for functions. If the bigger function goes to a number, the smaller function goes to the same number, the middle guy has to be trapped at that point. Sequences functions, the same idea works here. Limit n goes to infinity, an exists, and equals L. Like before, this gives me convergence of a sequence, even if I couldn't prove that fact before. Let's see an example of what a problem like this might look like and see where that gets us. So I want to find the limit of this sequence, sine of n times e to the minus n squared plus 3 minus 1 over n all squared. So at the start here, we're going to assume that we can use our limit laws. We're going to assume everything converges, and then when we get to the end and we actually get that they all converge, we'll be in good shape. So I'm going to now split this up into different pieces and see where that gets me. So if I split this up into two pieces across the plus sign, I get that I need to find the limit as n goes to infinity, sine of n e to the minus n squared, plus the limit as n goes to infinity, 3 minus 1 over n squared. Now this one over here is easy. This is a function, 3 minus 1 over n all squared. I can just plug in an x for that and take the limit like I would normally to get that this should go to the limit as x goes to infinity as a function of 3 minus 1 over x squared, which is 9. It's 3 squared, so it's 9. So that one's done. Let's now deal with the first one. This looks more problematic, and the issue being limit n goes to infinity, sine of n does not exist. Why doesn't that exist? Because it oscillates back and forth, up and down forever, and never goes to a certain value. So I can't use my product rules here to split this one up. But since sine is bounded between minus 1 and 1, I can use a squeeze theorem approach to solve this one out here. So what I know is that sine of n e to the minus n squared is bounded between e to the minus n squared and minus e to the minus n squared. Now as n goes to infinity, this goes to 0, this goes to 0, because those are functions that I can then just take the limit of because they are e raised to negative powers that are getting bigger, so it's going to 0. That means by the squeeze theorem, limit as n goes to infinity, sine of n e to the minus n squared is 0, which means it exists. Therefore, my whole process above was fine because these limits both exist. I can use my addition law to split this up into two pieces. And if I scroll back up, we get that we know this part here goes to 0, this part here goes to 9, therefore this whole thing goes to 9. That would be the answer for figuring out the limit of this sequence. So that's the idea of limit laws for sequences and how they can be used to evaluate limits of sequences. It's important to keep in mind that these laws only work when the sequences are convergent, and you may have to use Squeeze theorem for sequences to get that result to then be able to apply all these things together.